Antonio, and he will be presenting a benchmark collection of deterministic automata on XPath queries.
Is it working? Do you hear me well?
Yeah.
Okay, great. So today I'm gonna present a benchmark collection of deterministic automata for XPath queries. This is a joint work with Joachim Niehren done at INRI Alil in the context of my PhD thesis. So next in the presentation, I'm just gonna go through. Okay. Okay. So I'm gonna go through why we did this work and the why we did the choices we made along the way. Then pass to how we did it, and finally, if there is time, I'm gonna present quickly the benchmark results. So first thing first, why XML? Our main objective was to obtain small deterministic automata to be used in automata-based streaming algorithms for structured or nested data. And what better than XML as a candidate for that purpose? So there has been extensive work and research on XML stream, whether for validating, sorry, querying and transforming XML stream using XPath, which is the core language of the languages for XML data processing, like XSLT and XQuery. You can find a wide range of theoretical results there with different complexity and different coverage. So most approaches work fine in memory evaluation, but when it comes to streaming mode, it becomes really tedious, especially when it is syntax based. So the second why is, why did we choose automata? Mainly it can provide a full alternative to syntax-based approach and most of the other approaches. And they are easy to obtain from regular XPath queries. So algorithmically, it's a bit tedious, but computationally it's easy. And most importantly, it provides the largest coverage of XPath evaluation on XML streams. I'm gonna cite a few works quickly here that used automata. So the one of Olteanu that used transducers, which are automata with some output tape. The work of Muzaffari in the context of complex event processing of XML streams. And lastly, the work of Sebastian Niehren and Mr. Zarqawi. So mainly, one thing to mention about this last work, it used networks of nested word automata, and it covered almost with few minor exceptions, full XPath 3.0 at that time. Okay, so we chose automata. Why it has to be deterministic? So for simple reasons that it has a better complexity in solving algorithmic problems, in particular universality problem, which is the problem that we are interested into. And the ability to obtain unique minimal automata of course, up to renaming the states. And there is also a lot of work in this direction using deterministic automata. I'm gonna also cite a few. So like the one of Gauvin and Niehren, they also used, sorry for many automata models, they also used the nested word automata, the work of, a more recent work of Schweigart, which in the context of evaluation on compressed documents. And the most recent one is, this year, is of Reveros, where they used visibly push-down transducers that extend on visibly push-down automata and provided the solution for enumerating answers on streams of nested documents like XML or JSON in what they called output linear delay. So if determinism is our best or our better solution, what's the problem then? Well, they are actually difficult to obtain. And this is because computationally they come with a high complexity, they are exponential. Sorry. They are exponential in the worst case. So when our colleagues back then in the works I mentioned tried to compile XPath queries, even simple ones like descendant A / descendant B, there was a huge blow up when constructing this automata in the size of millions. So you can clearly see here, for example, this query that is relatively simple. It will give us an automata of size 20 million with 5,000 states. So after that, we used another approach where we could convert nested word automata to stepwise hedge automata. So it's another model. Determinize it and go back to nested word while preserving determinism. We were able to obtain the needed small deterministic automata for the whole regular part of XPath mark benchmark. But again, when we started to go a bit further from this benchmark and test other query, the blow up came again. And so here's another example of a query that we tried to compile directly to stepwise hedge automata. And it went up to 1.6 million in size with 10,000 states. So we needed to find a solution to have this automata small to be manageable. Well, the key thing was to use the schema, which I'm gonna show next. After that, sorry. So, as a contribution, we provided a collection of deterministic automata for the regular part of Lick and Schmitz benchmark. This is a practical benchmark where they extracted XPath query from different online programs like DocBook, HTMLBook, TEI, and all of that, more than 20 programs. It was around 21,000 queries. So the regular part of it, it's 4,500. We used a recently proposed technique to include the schema in the process of determinization and applied it on the stepwise hedge automata. And we tested our automata for correctness relatively to Saxon. So let's get a bit into details because too much storytelling before. So I mentioned the universality problem before, and it was for a reason. So if we can take this simple example on words first, and for those who are familiar with the finite state automata, this should be straightforward. Is it okay? Good. So this query is mainly saying verifying if a word contains a letter A followed directly by a letter B, that is followed eventually by a letter C. And this is the automata that represents this query. So a run should start at initial state here, read the letter a state by state, so we start at 0, and then move depending on the letters. So here comes the run reaching C. So we started 0, read 1 at A, read another 1, we remained at 1, read another A, sorry, we remained at 1, read it a C, we went back to 0 because actually we are waiting for an A directly followed by a B, read a A, read a B, and then read a C and reached state 3. So state 3 is what we call a universal state, and this is our stopping condition for an algorithm, whether it's for a Boolean query or for a query that is selecting nodes. So once I reach a universal state, I can decide that, okay, I have an answer for that query. And this is why we are interested in this problem, because in case of deterministic finite state automata, it can be done in linear time, where it is space complete in the case of non-deterministic. And even the non-deterministic case gets worse when we go to nested words or nested structure like XML and all of it. So I kept saying nested words, nested words, nested words, automata. So the nested words are actually the are actually the abstract model that we use in order to compile XML to it. It's fairly simple. It's actually a well-bracketed word, but our notion of nested word, excuse me, our notion of nested words is a bit different in the sense that it is not tagged. Instead, we rely on words from the signature with the concatenation operator. So if we're gonna represent XML like a nested word, it would be like this. So firstly, the document node that's almost everywhere. And then an opening bracket, LM site. Then we open a bracket, LM closed auctions. And whenever an element ends, we close the brackets accordingly. So since once we have nested words, we can use all the machinery we have from automata and others to work on it in the literature. So our choice of automata was stepwise hedge automata. It generalizes on both words and trees, and therefore on sequences of nested words. It can read sequences of words, trees, and so on. It avoids top-down determinism, so the blowup, it's, let's say, less severe. It has the same expressiveness as nested word automata. And the universality checking, so the universality problem there can also be decided in linear time. So it can be a possible alternative for streaming algorithms on nested words. Here comes one stepwise hedge automata. I'm not gonna explain the model on this one, but on the one next to it, the one representing the XML model. But just to say, this one is just for variable binding, so it allows to bind a variable x once, and we're gonna see how in the next slide. So this is the automata that represents the XML model and allows to select nodes. while running. So for the part that is still in color, so let's start with the first branch here. So this branch is what we need to read the an XML attribute. So again, if you are familiar with finite state automata, you are halfway there. So we start with a 3 initial states, so it's actually opening of a nested word. We read the type attribute, any namespace from the signature, so it's the prefix of the namespace, any name, which is the local name of the attribute. Then here, we either bind a variable for selection, if we're gonna select this attribute for the query, or we don't bind it, so 2 paths. And we end up in what we call, okay, and also read the value of the attribute in a series of characters. And then we end up in what we call 3 states. So this is new normally from finite state automata. So here the whole branch read a whole nested word of type attribute. It ends whether in 24 and 23. And this is how it becomes relevant next. So back down to the down branch. So we are now reading an XML element. It goes the same way, type element, prefix of namespace, any name, local name, either bind or not bind the variable. And if you can see here on state 16, you have a transition 24. So this actually means that here I can read a whole tree or a whole nested word that could be evaluated of state 24, which we just saw earlier. It means I can read an attribute here. And you can continue like this. So the whole automata here can represent a document that can be run with this automata correctly and accepts. It means it's well formed and it can select nodes during the run. So let's see quickly the compilation chain. So how did we obtain this automata? So here comes also a simple XPath query, which is selecting a node called body that has an attribute lang that is not empty. So we first compile it to nested regular expression. So regular expression are there since decades. I'm not gonna get into details, but what I need from this is to notice that after like the type lm, the namespace h, the name body, we have here this variable x, which is marking that the node body, this node body is to be selected. So this query will actually give us or detect the body node. And now, so here comes the nested regular expression that is compiled to our stepwise hedge automata. This one is non-deterministic. So next we're gonna see something ugly, so since we are in a beauty context here. So this is the automata that is compiled directly without any schema, determinized directly without any schema. So it's not supposed to be read, but just to show how ugly it is. It's the right amount of ugliness that fits in one slide. Actually, this is not very big. So I think tens of states and maybe some hundreds of transitions. But when it goes up to millions and you need hours on a simple laptop to get such an automata, it's practically unusable or useless, let's say. So, and here comes the beauty. So this one should win. This is the same query, but we integrated the schema within the the determinization process. And we were able actually to obtain really small automata, and if I reach it, I'm gonna show the result at the end. So here comes the results, the setups. So the benchmark setup, we first compiled an XPath query to stepwise hedge automata, so this A here. Then we attempted to determinize it. After it determinized the product, so the query automaton with the schema automaton, so XML model schema we saw before. Surprisingly, we thought that it will also explode even more than the query alone, but it didn't. We kind of have an intuition why it didn't. Here comes the determinization using the schema with the approach I talked about earlier, schema-based determinization. Then we minimized both of them. I'm gonna come next to minimization. And finally, we compiled it back to nested word automata. So before going directly into the result, just few words on minimization. So minimization algorithms for automata already exist for the finite state case. They can be lifted to stepwise hedge automata, and the resultant automata is actually unique under some prerequisite properties that I'm not gonna get into it. And we did implement the minimization algorithm also to further reduce the automata that we obtained. Sorry. So finally, here comes the result. So in the first, so this is let's say 4 or almost 10 queries of the full benchmark from the paper. The first column represents the size, and as I said before, inside the parentheses are the number of states of the query directly compiled to non-deterministic automata. They are not relatively that big, but still hard or big enough to be determinized. And because next you will see when we attempted to determinize them, so the empty boxes here, we could not obtain this automata with a timeout of under 100 seconds, if I recall correctly. So 37% of them were not computed. Next, as we said, sorry. We determinized the product with the schema, almost done. And they were most of the time smaller, at least in the number of states. And next, here comes our schema-based determinized automata. And they were smaller, mainly roughly by a factor of 2, and most of the time. We minimized both of them with the minimization algorithm I just mentioned earlier. And the one with our approach mainly led to the smallest size, and it was an average, I think. So at the end, for the whole benchmark, we got automata with 27 state in average and 70 transition. And finally, we converted it back to nested word automata, which preserved determinism and were actually small. So just to conclude, so we provided the collection of deterministic automata from the practical benchmark, The results are free online for both stepwise hedge model and nested word model. We are working now on a streaming algorithm that it's in progress that is using this the stepwise hedge model, and as a direct application would be on XML streams. And we are thinking about the possibility of lifting these streaming algorithms to hyper-streaming. And that's it. Thank you.
Thank you very much. We have 1 minute for some question.
I think that's really interesting. I just had a doubt about one thing. So it's the hedge automaton. So
it's a stepwise hedge automaton. So hedge automaton.
I just have a doubt about hedge.
Yeah. So
whether or not you meant edge.
So hedge automaton, I think you're talking about the work of Murata. I think so. There is the.
Just thinking about the word hedge, because it's because in French you don't pronounce the H's, and I'm wondering whether or not edge wasn't. Is it the edge of something, or is it?
So hedge, so H-E-D-G-E, so like a
so
string of
words. It isn't in A.
Sorry, I'm not.
So I could be wrong, but I thought that maybe that there might be a confusion on there.
No, it's hedge with the H.
All right, so my mistake. Thank you.
More question? Okay. Thank you very much.
Thank you
very much.
Okay, you need this.